So here we learn how to write functions in octave. So this is the octave screen. So we have make this as our current folder, current directory or current folder where we will be writing our programs. If you put dir command, so you will see what current files are there, what are the files there in this current folder. So this is the command window. So let us write a program. Say suppose C equal to CLS. CLS means clear screen, clear all. That means all the workspace variables will be cleared. Now suppose A equal to 2 and B equal to 3 and C equal to A plus B and D equal to A multiplied by B. So if you save this program, give it some name. So here maybe XXX7. Save. So if you run this, save file and run, then the results will be displayed in the command window. So A is 2, B is 3, C is equal to 2 plus 3 and D is equal to 2 minus 2 multiplied by 3, which is 6. So and you know that if you put semicolons after these statements, the results will not be shown on the command window. Anyway, now suppose we want to write this in a more compact manner. Then what we can do, we can use a function. How? So we have to now write a function that cd equal to add mul a p. Okay, and we have to save this. And we have to open a new script file where we have to define a function cd, where cd are the outputs of the function, and function will be here. Function cd is equal to add mul a b. So A and B are the inputs and C and D are the outputs. So here let us write C equal to A plus B and D equal to A multiplied by B. But remember that this function has to be saved as add mul, which is same as the name of the function. Now here we can call this function and see the D will be generated. So now you can print C and D, or let us write A, B, C, D. So let us give some values to A equal to say 2, B is equal to 3. Okay. So now if you run this, so see, so A, okay, let us put okay, so this is here we put a semicolon and then save it, and here, so let us put semicolon here with so many values are coming that you will get confused. So now this is saved. Star means is still not saved. So you save this and you run. So in the command window, C equal to 5 and D equal to 6. So C equal to 5 and D equal to 6. Go to editor. Okay, put a semicolon here and again you save file and run. And in the command window, you put A equal to 2, B equal to 3, C equal to 5, D equal to 6. So in this way you can write functions. Now also what you can do, you can give say E F equal to add mul 7. So and you delete this and write E F. So run, save file and run. At the command window you get E. Again here you put semicolon and then run, and in the command window you get E and F. So in this way you can write functions, so where you can make your programs look simpler. So now how can we use this in this program? Suppose we open here file, open say xxx maybe 6 5, we open. So this, okay, not this one, file, open x664 maybe. Then here see, this is what we did in our last class. So for two elements, so this was this problem. Just remember there were two elements like this, and we computed the element stiffness matrices and assembled them and got the system stiffness matrix. Now if we save this, say save file as say xxx, which this is the seventh file, xxx8. Okay, save. So this is so what is happening here, we have saved it as xxx8. So what is happening here, there is a loop over elements. For the first element, this is the first node, this is the second node, this is the length of the nodes, this is the length of the element, this is the cos, this is so this line I put, so this is cut and I put here, that looks better. This is the cos, this is the sine, this is the initialization of element stiffness matrix, this is the property index, and this is the area which we are retrieving from the property array, and elasticity, modulus of elasticity we are retrieving from the property array, and this is the element stiffness matrix. So what we can do is, now we can take this whole thing in a function. So cut and file, new script, let us paste it here. Okay, and call it say function k element equal to, say we name the function as stiff, and what are the values to be input? L naughts, obviously, L xc, L prop, L prop, L prop, yeah, L prop should be there, prop. Okay, now see, if L naughts is there, we can get N1 and N2. Once we get N1 and N2, XC is there, so we can get this length. XC is there. Now since XC is there, we can compute C and S. Then this is the initialization. This is L prop. L prop is coming from here, and it is taken from L naughts. So this is not required. L prop is not required because once you know L naughts, you can get L prop. But what you do not know is the L num. L num is the current element number. How does this function know the current element number? Here also you do not know L num. So L num has to be given as input. But L prop is not required. If you give L num, then L prop it can get from it. Okay. L num and L prop it can. L num is coming from here. If you give L naughts is coming from here. So from here you can get L prop. L num is the current element number and the loop is going over the elements. So you can get area from property. Property is coming from here, and you can get E mod from property. Property is coming from here, and you can compute K element, and this K element is going as output. Okay, so let me save file as, say, stiff. Save file as stiff. Save. And okay, and here this first statement you just make a copy, and you paste here. But here you don't have to. Okay. And you can give it some other name like KL, because here using KL as element stiffness matrix. So KL equal to stiff. So L num is going from here, L naughts is going as input, XC is going as input, and prop is going as input, and it is computing this. So if you just save file and run, then see what we are getting in the command window. So see, we are getting the assembled stiffness matrix as we have got in the previous case where there were no function defined. So it is giving you, so K element it's giving, and KL it's giving editor. So you put this here, okay, not here, just here you put semicolon, it will not print this. Don't forget to save this. Once you save, the star will go, and this is still unsaved. So run, save file and run. So now in the command window, this K element is not coming. So see, so now your program looks more organized and it's easy to understand also. So it is a loop over element. you are computing the stiffness matrix for the current element. Now you are assembling and you are going for the next element. So the next element, and you are coming here and you are going for the next element. So for two elements there is a loop, and in the loop first it is computing the element stiffness matrix for the first element. It is assembling it, that is putting it in proper place in the assembled system stiffness matrix. Now again for 2 it is again putting it in the assembled system stiffness matrix, and where there is an overlap they are simply adding it. So in this way you make your program look much simpler. Now what about the boundary conditions? So boundary condition is, so here what are the degrees of freedom? So at degrees of freedom 1 and 2 it will be fixed hinge, and at 5 and 6 it is hinged. So you put in the editor that in the assembled stiffness matrix K, so there is a large number, so let the large number be the K11 multiplied by 1E7. Okay, now you put K11 as L, K22 as L, and K55 equal to L, and K66 as L, and your force is equal to, force vector is, since the displacement there is 0, so here you put large numbers here and large number into 0 in the right hand side. So force here, so the force would be 0, 0, and what are the forces here? 500 and 1000. So 500, 1000, then again 0, 0. So you can have a look, you can run this and have a look. So in the command window, so F is this. Now what you have to do is you have to get the solution, that is, suppose you solution is, say, displacement equal to K, this is the command. Okay, so this is small k, yeah. So this is the solution. So let us put it here in the editor. Do not put disp as displacement, because disp is already a library function. So disp equal to k, disp equal to k f. So if you run this, save file and run, so in the command window you will get this. So this is the displacement. So here hinge 0 displacement, hinge 0 displacement. This is in the degree of freedom 3, this is in the degree of freedom 4, this is degree of freedom 5, and this is degree of freedom 6. Now if you want to get the forces, then again you start a loop over the number of elements. Okay, again a loop over number of elements. Now KEL again equal to stiff. Again you just call this function to get the system stiffness matrix. So you have not saved the system. You have not saved the element stiffness matrix. So you have to again calculate it. So this is the systems. Semicolon here. So this is k element. Now, so for this UG, that is for the first element, what will happen for the first element? For the first element, what are the displacements? For the first element, the local DOFs are LDOFS. So this is, and this is DISPL, or you can just simply write DISPL. So here LDOFS, LNum is the element number 1. Okay. Then here just repeat it, copy, so comma, paste, so LNum 2. That is, what is the global degree of freedom for the local DOF1 in element LNum? Element LNum, local DOF, what is the LDOFS will give the global DOF, and from this DISPL that value will be taken. So here DISPL, okay, paste, okay, comma, paste, and in place of comma you put semicolon, because it is a row vector, sorry, it is a column vector, so you put semicolon. It is semicolon. I think it is okay. So let us try it out whether there is some error or not. So save file and run. So yeah, so see, for this -2 is almost 0, -0, 0. So for so for element 1, that is, this is for element 1, there is some problem here, because it should be 0 0, then this and this. For this it's okay, this again is 0 0 there. So I must have made some mistake. Yeah, the mistake is 1 2 3 and 4. Local div 3 and local div 4. Now let's see. Run, save file and run, and in the command window now it's okay. 0 0 this 0 0. Now what happens if you just here, okay, then if you want to get the element forces in the global coordinate, so see these are all in the global coordinate system. So Fg would be KL multiplied by UG. So now you get the forces on each elements. Now save file and run. So here in the command window, so these are the forces on the first element and these are the forces on the second element. So see, the equilibrium is maintained. Equilibrium x0. So y, yeah, so equilibrium is maintained, and this is the left reaction. These two are the reaction from the left end, and these two are the reactions from the bottom end, right bottom end. So in this way, see, by writing in this way, just by writing a function, how we can make this program looks nice. Otherwise there would have been a lot of statements and the clarity of the program would have got lost. So thanks here for your patient hearing. So let us stop here.